Good morning, everyone. Welcome to the SIBGRAPI technical section, Datasets and Classifiers, is TS6. My name is Jorge Cavalcante. I'm from Federal University of Pernambuco, and today I'll be the chair of this session. In total, this session has 6 presentations, and all of them were previously recorded. So the first step is the recorded video will be presented, and after we have some time for questions. Please submit your questions as soon as possible on YouTube or the Discord channel. The first paper of this section is entitled Iterative Pseudo-Labeling with Deep Features Annotations and Confidence-Based Sampling, and it will be presented by Barbara Benato.
Hello everyone, I'm Barbara Benato. I'm going to present our paper entitled Iterative Pseudo-Labeling with Deep Feature Annotation and Confidence-Based Sampling at SIBGRAPI 2021. So first, the success of supervised deep neural networks is evident in many applications. However, the need for large annotated training sets is a well-known problem. For this, same-supervised learning, pseudo-labeling, meta-pseudo-labeling, and few-shot learning methods have been investigated to address this problem. Pseudo-labeling and meta-pseudo-labeling have received increased attention in the last year. Pseudo-labeling approach is essentially adopt a same-supervised strategy with the apprentice model, assigning uncertain the pseudo-labels to unsupervised samples. The model can be retrained with large annotated dataset by assuming that pseudo-labels are actual labels. And meta-pseudo-labeling uses an auxiliary model, the picture, to generate pseudo-labels to train the primary model, the student. Yet, pseudo and meta-pseudo-labeling methods still require a training set with hundreds of supervised samples per class and a validation set with extra supervised samples, at least other 1,000 labeled samples to guarantee reasonable label propagation accuracy. In this work, we improve an iterative meta-pseudo-labeling strategy named Deep Feature Annotation, DeepFA, that uses only dozens of supervised training samples per class and does not need an extra validation set and step with supervised samples. We propose confidence DeepFA, DeepFA, by using the confidence of the auxiliary model used for label propagation to select these unsupervised samples for training the primary model. In this paper, we explore the confidence of OPF-SEMI to select the most confident unsupervised samples to retrain VGG16 in the next iteration. So the first question that we want to answer is, does the confidence-based sampling improve the DeepFA? In this figure, the results for kappa and propagation accuracy are shown for the studied datasets and with different ways of selecting the confidence threshold. For datasets with higher kappa values, we note that DeepFA obtained similar results compared with our proposed conf DeepFA modifications. However, we see a gain of almost 5% in kappa and propagation accuracy for the most challenging datasets. For protozoosis with impurities, the gain is actually higher than 10% in kappa and 17% in propagation accuracy. In short, our proposal of using DeepFA with OPF-SEMI's confidence sampling obtained the best results for most tested datasets. The next question is, does the confidence-based sampling improve DeepFA along the iterations? This figure shows a mini dataset along 5 iterations of conf DeepFA. We see that both kappa and propagation accuracy slightly decrease after the third iteration. This may suggest that the proposed method saturates the learned pseudo-labels and the original images can be used as input for a better and known deep architecture. In this figure, we plot training and validation losses and accuracies during MNIST training. The learning curves show that labeled samples can improve the network convergence along the iterations. In conclusion, we proposed an approach for increasing the quality of image classification and extracted feature space when using very few supervised samples. To improve label propagation accuracies and classification results, we include a confidence sampling strategy, two OPF semi-pseudo-labeling to define the most confident samples for training VGG16. Our results show an improvement in propagation accuracy and kappa, and considering OPF semi with the confidence sampling strategy, and this choice may depend on the dataset. Thank you for your attention.
Thank you, Barbara, for the presentation. Now we can go to some questions. I would like to ask you a question. Could you explain a little bit more which the role of the TSNE in your architecture? The TSNE do you want to reduce the dimensionality in order to see some things, or just to reduce the dimensionality? It was not clear for me.
Yes, good morning, everyone. Good morning, Professor. Thank you for the question. We see in earlier experiments that the label propagation accuracy, when we do that in the feature space projection made by TSNE, get more interesting results than the feature space provided by ND space. So we are using TSNE for dimensionality reduction for label propagation, increase the label propagation performance in this case.
Okay, and how do you define the size of this dimensionality reduction? Was by experiments, or you define some range?
The original case, the people use TSNE, we reduce the dimensionality reduction for 2.
Yes, it's good to reduce for 2 because you can see it in a plot.
Yes,
yeah. Yes, that was my. And thank you for the answer. Let me see if we have some more questions here. Moacir Ponte has a question here. Thank you for the presentation, Barbara, and you show some examples of saturating results along iterations. Is it possible to compute an ideal, best as possible, oracle that can offer an upper bound result?
We are thinking about this situation, what could be our best result. We consider to compare in our future works the VGG16 trained with all samples available. We think that this could be our upper bound. Of course, we could use the true labels and to train the VGG16. This could be our best case.
Yes, and he also says that this would allow to better understand how close the method is from achieving the highest improvement in results. It's like to have a really upper bound, of oracle that could say, here is the top.
Yes, for sure.
We don't have more questions. Of course, we can continue this discussion after in the Discord channel. And thank you, Barbara, for the presentation. We can move on for the next presentation. The next paper, the second paper of this section, is entitled Reducing the Need of Bounding Box Annotations in Object Detection Using Image Classification Data, and will be presented by Leonardo Blanger. Leonardo, please correct me after the presentation. So we can start.
Welcome everybody. This is the presentation for the paper titled Reducing the Need for Bounding Box Annotations in Object Detection Using Image Classification Data. My name is Leonardo and these are my co-authors. So to begin with, this work deals with the problem of object detection. And one realization we have is that acquiring labeled data for object detection is expensive, or at least it is more expensive than for traditional image classification. That's because we need to provide class labels as well as bounding boxes for a variable number of different objects which can occur at random positions and random scales within the image. And in this work we attempted to attack this problem through the idea of data synthesis. That is, can we generate artificial labeled samples for object detection? And most importantly, can we do so without needing even more expensive supervision? And I mentioned this last part because a common feature of existing data synthesis approaches for object detection is that they tend to depend on segmentation masks of the objects. Therefore, they do not really help reduce the need for expensive supervision, as masks are even more expensive supervision than bounding boxes. In contrast, acquiring labeled data for image classification is cheap because we only need the class information, and as a consequence, data for classification is usually available in much larger quantities. And this leads us to the motivating question for this project, which is, can we take advantage of image classification data in such a way as to improve the sample efficiency of object detection models? And by that I mean needing less detection-specific labeled data. And can we do so without needing any more expensive supervision? And here by more expensive I mean anything costlier than just class labels. And the approach we take in this project is the following. We attempt to use classification style images to generate artificial or so-called fake detection images. And in this sense, existing approaches to this problem, they follow a very simple strategy. They just crop the region of interest of the object from existing object images, and they paste these regions randomly on top of background scenes. This is also the strategy we're going to follow on this project. However, the problem is that they need a segmentation mask of the object regions to do this cropping. So this approach, in its basic naive form, does not really help reduce the need for expensive supervision. And that's one of the problems we try to solve in this paper. Another question that emerges when trying to use artificial samples is how best to incorporate them on the regular training process of a regular object detection model. And here, existing approaches don't really investigate these in much detail. They simply mix these artificial samples with the real data. But here, we propose a different strategy. We propose to use artificial samples to pre-train detection models before fine-tuning them on purely real data. And our claim here is that this serves as a powerful initialization strategy, and this will lead to the model achieving comparably good results using less real labeled data during the fine-tuning stage. And this is the claim that we evaluate on the experiments. The contributions of this paper are the following. First, we developed a simple method by simply combining already existing techniques that was capable of generating artificial samples for object detection. And that it did without using any expensive supervision besides just classification labels. Also, we performed a systematic evaluation on how useful these artificial samples are on the problem of object detection. And here we note that better results are achieved when pre-training detection models on these artificial samples, which in turn allows us competitive results using significantly less real labeled detection data. And the main conclusion of this paper, which sort of ties everything together, is that we can take advantage of cheap classification data plus a few detection samples to obtain a strong baseline detector. That's it, thank you. Hope you watched the full presentation. Goodbye.
Thank you, Leonardo, for the presentation. And I have here at the YouTube a question about. The question was posed by Claudio Young. How do you compare the proposed approach with weakly supervised object detectors that also use only classification labels?
Okay. I'm not very familiar with techniques for weakly supervised detection. I'm assuming that the way they work, they also train detectors using mixed classification and detection data. Please correct me if I'm wrong. I guess they are complementary approaches. The main takeaway from the project we had was the capability of using fake samples to initialize a model. What you do to train the model, post initialization, the fine tuning stage, I think it can take advantage of any improvement, any better strategy for regular training. Or they can be trained using only classification labels. Yeah, if they can be totally trained using only classification labels, I'd say they are a step in the same direction then.
So you have the labels of all the data to perform your architecture, because when we are using using weakly supervised object detection, weakly supervised, we have some parts that are not labeling. And Moacir Ponte also highlights some information here. I will read for you. Maybe using a self-supervised learning approach to pre-train, it will be even cheaper than use actual labels, real data, on the second stage of your architecture.
Perhaps so. So yes, again, this is I think that is also something worthy to be further explored. The main takeaway was the initialization strategy, but I think that's also a valid follow-up.
Yes, and I believe, Leonardo, that your main contribution is about the idea of generating artificial data and including the image and after to use this kind of information in order to improve your whole system. But of course, the questions are posed by Moacir Ponte and Claudio Jung, you should consider in order to have a bunch of information in the future world.
Absolutely.
Thank you for the presentation. Thank you for answer the questions. We do not need any more questions here at the YouTube. So
Thank
let's
you,
move
Jorge.
on. Thank you. So the third paper of this section is Data Augmentation Guidelines for Cross-Dataset Transfer Learning and Pseudo-Labeling, and will be presented by Fernando Santos.
Hi, my name is Fernando Pereira dos Santos, and I will present the main points of our paper, Data Augmentation Guidelines for Cross-Dataset Transfer Learning and Pseudo-Labeling. Gabriela Tomé and Moacir Ponte are also authors of this paper. In our study, we investigate the saturation of data augmentation methods and supervising learning influence for cross-dataset scenarios. Different levels of saturation to generate synthetic images using data augmentation methods for the search dataset were performed. Then, we fine-tuning the ResNet 50 use all this data. A different dataset is used to test the classification model. The methodology consists to establish any images for a training set use a data augmentation technique. Each image in the original set can be used to generate until 5 different synthetic images. If self-supervised learning is applied, the synthetic images receive a pseudo-label different from the original images. For example, if in the training The blur techniques use original images receive the label 0 and the synthetic images the label 1. So we fine-tuning the network to distinguish both classes, originals and synthetics. We perform the conventional fine-tuning to classify the original labels and evaluate using the test set. Our alternative data augmentation methods are blur, correlate, noise, and sharpen. These methods are different implementations for image manipulation, adding distinct methodologies of noise and other operations. Blender, threshold, and visual smooth are methods which perform combinations of images from the same class. We compared our alternative methods to traditional ones: flip, rotation, and shift. The main results are: if you have datasets with few classes in cross-dataset scenarios, self-supervised learning can be used as warm-up stage to improve final performance. Data augmentation that only performs pixel manipulation is to provide good results, and a massive increase of the training set without variability is not guarantee of better performance. In conclusion, we investigate 6 new augmentation techniques with high potential to improve cross-dataset prediction scenarios, exploring saturation and self-supervised learning. In our results, increasing the training set progressively has no guarantee of better performance. Our methods can be applied for transfer learning scenarios, mainly in small datasets. Thanks.
Thank you, Fernando, for the presentation.
Hi, thank you.
Thank you. I have a question. Let's wait for some questions at YouTube, but now I have one. You use the 6 data augmentation and different data sets to perform cross data set transfer learning. And do you observe some correlation between some data augmentation techniques and data set specific, or do you believe that you should really use these 6 ones, or select a subset of them?
Okay. Thanks for the question. Actually, we test several different methods, but the method which only performs manipulation of the pixels, it's better for these scenarios. Methods which combine some images from the same label, it's not very good, but it's also better than the conventional ones. And we can see if we have some class with few examples, the combined methodology is not good because we have no different image to combine. So we can choose, for example, to the simple method. It's better for the scenario.
Okay, thank you. I have a question here at the YouTube. So, Claudio Young, nice work. How to define the magnitude of each augmentation primitive? Did you explore any policy for determining the optimal combination, as in rand augment, for instance?
No, we only explore the potential of each methodology. As a future work, we're going to explore more details from each methodology and different data sets. Thank you for the question.
Mateus also has a question. Mateus Barros, is there any idea of how well would the approach work for dense tasks such as semantic segmentation?
No, we only try to classification images, but of course we can try to apply the same methodology for different tasks such as segmentation. I see no problem in to adapt these methods for this task, for example.
David Menotti also asks you, and besides facial expression recognition, are there other problems where this approach is suitable? small data sets or small number of classes?
Yes, the methodology using a combining method, it's not very good if you have few examples for classes because we don't have much data to combine. So the result syntactic set is very not different from one image from others. And then if we have a more example in the same class, and the methods perform better.
Thank you, Fernando. Thank you for the presentation. Thank you for answering the questions.
Thank you. Thank you.
So let's go for the next paper, and the paper STN PLAD, a dataset for multi-size power line assets detection in high-resolution UAV image, and will be presented by André Luiz Buarque Vieira Silva.
Hello, my name is André. I'm here to present STN PLAD, which is a dataset for multi-size power line assets detection in high-resolution UAV images. This work has been done in partnership between Universidade Federal de Pernambuco, Centro de Informática, Voxar Labs Informa, and STN. So today, defective components are the main problems for power lines and power line companies. They can lead to various issues such as power cuts and completely overthrow transmission towers. So it's very important to keep the inspection process up to date. However, as you can see here, this process can be very risky and unsafe for the inspection workers. So we aim to automatize this process by doing image analysis on power line assets. However, today there's a huge lack of power line assets data online and public. So this work goes in this direction to try to solve this gap by gathering new data on power line and power line assets. This is our team that went on field to collect this new data with UAVs, also known as drones. And we compared our data set with the ones available today. And we noticed that there is a huge gap on the public data sets available today, which are those two, one on the left and one on the middle. They are only regarded one power line asset type, which is insulators, and they're not on the real world scenario. On the other hand, our data set here, you can see there are many type of assets, and it's contained on a real world scenario. Here you can see a few sample images from our data set. These are very high resolution images, so there's a lot of information here. And this is our 5 power line assets types today. They were annotated with those tags: towers, insulators, spacers, ID plates, and dampers. As you can notice, these objects vary on size immensely, so that makes general purpose object detectors performance to be very limited. For evaluating our dataset, we used 2 main object detectors technique recommended by the literature specifically to this application domain, which were SSD and faster CNN. With these results we achieved with those 2 object detectors, we are able to propose a pipeline, which we call MSPAD, to improve the performance. Here is the final result compared to the SSD, which performed better than the faster CNN, and our pipeline MSPAD, which achieved a 89.2% mean average precision. Here you can see some qualitative results regarding those detected objects, such as towers, insulators, spacers, ID plate, and dampers. Finally, the S10 FLAD is a new public, real-world, high-resolution, multi-asset Powerline dataset. It's made public. It's public today on GitHub. You can download it, start applying, and developing new object detection techniques to it. Just feel free to do that, and feel free to contact us. Our current baseline is 89.2% MAP. So this is the link where you can download the dataset today from GitHub. And if you have any questions, you can contact me on this email. Thank you.
Thank you, André, for the presentation.
Thank you, Professor.
Thank you. And you said that the datasets are already available for public assessment. And you intend to continue to update this dataset, or it's a version 1 and the work continues? This is the question.
Thank you for the question. I would like to thank you and also point out that we invite that the previous works, the previous authors from the previous works can apply their techniques on this data set. I believe some of them can benefit from this public data and can validate their methods with this data set. And then to answer your question, yes, we intend to continue to improve this data set and to increase the total number of images of it and in time. And also increase the total number of assets as well.
And about the other works in this session, I can see an intersection that you can also use to improve and to have more images in your data set, because you're talking about augmentation, something like that. And
exactly.
This will also improve to maybe to detect the next detector or the next deep learning technique that you will use in your PhD, okay?
Yes, perfect. Thank you.
Let me see if you have some questions here. No, we can continue the discussion on Discord. Thank you, André, for the presentation.
Thank you, Professor.
Oh. So we have a question at the chat, but we can discuss at the end of the section. Okay, now we move on to the next paper. That is semi-supervised CMEs network using self-supervision under scars. Annotation improves class separability and robustness to attack, and will be presented by Gabriel Cavallari.
Hi, this is the brief presentation for our work. This work was done by me, Gabriel Cavallari, and Professor Moacir Ponte. As a motivation, we know that deep convolutional neural networks have been successful in computer vision thanks to their ability to learn high-level semantic visual representations. But they mainly follow the supervised learning paradigm, which requires large amounts of manually labeled data, which are costly, time-consuming, complex, and expensive to obtain. And some real-world applications require classes that are not present in standard large-scale benchmark datasets. Therefore, it is important to investigate strategies that learn without or under limited annotated data, for example, using self-supervised and semi-supervised learning. In this context, learning from limited data can be tackled using a combination of semi-supervised learning and self-supervision. In our work, we combine the traditional supervised learning paradigm with the rotation prediction self-supervised task. In particular, we are interested in the case in which the proportion of labeled with respect to unlabeled data is small. We compared the effectiveness of this method on 3 different image domains, also studying the robustness of the method to noise in the form of one-pixel attacks. We show it is possible to use unlabeled data to obtain more discriminative and more robust representations compared to the supervised baselines when evaluating the resulting feature spaces. This is an illustration of our work. Labeled images are used to train a classification-based CNN, as shown in blue. Unlabeled data is used to learn an auxiliary task, in this case the rotation prediction task. You can see that the CNN backbone share weights with both the supervised task and the rotation prediction task, And the resulting feature is the 128 dimension embedding. So our semi-supervised method considers a joint classification loss to train a Siamese network, where both labeled and unlabeled losses optimize across entropy loss function. We assessed the performance of our method on 3 different datasets, STM10, fashion eminence, and malaria. So in our experiment setup, we test 3 CNN backbones. And for the supervised experiments, we use either 1% or 5% of labeled data. For the semi-supervised experiments, we add unlabeled data. When pixel tags are produced assuming access to the training data. For the evaluation, in order to evaluate the discriminative capability of the learned representations, we employed a linear SVM on the 128 dimension extracted features. Here are some of our results. The delta represents the difference between the accuracy of the semi-supervised model and the supervised model. In this table 1, we can see the linear SVM test accuracy of the SL10 dataset when using 1% of labeled data. We can observe that for the MobileNet V2 architecture, the performance for the supervised model is random. In the semi-supervised model, we have good improvements and the performance is much better than the supervised model. We can observe that in general, the performance of the semi-supervised model is better than the performance of the supervised model. For the fashion dataset, when using 5% of labeled data, the semi-supervised models always perform better than the supervised models. For the malaria dataset, using 1% of labeled data, here we can also observe that, in general, the performance of the semi-supervised model is better than the performance of the supervised model. Discussion. We showed that overall, the semi-supervised network was able to improve results over the supervised version. CNN backbones that were not capable to converge using only supervised learning were significantly improved by using the unlabeled data. And for the biomedical image domain, there are 2 main important observations. First, because the images of malaria are not angle-oriented, the rotation task becomes harder. Second, the attack had an even stronger impact on results due to the nature of the image that contain patterns that are similar to the attack. As a conclusion, we can say that self-supervised learning demonstrates to be useful in semi-supervised scenarios, not only to improve the numerical results, but in particular to learn more discriminative spaces, as well as a representation that's more robust with respect to attack. The choice of auxiliary task must take into account the nature of the images and may not suit all applications. However, the mere introduction of unlabeled data into the training process significantly improved minimal data learning cases. Thank you for watching.
Thank you, Gabriel.
Thank you.
And I have one question. Why did you decide to use a linear SVM?
Well, we decided to use it because it's a shallow classifier and it has some learning guarantees. So we could also use, for example, just a linear layer after the expected features. Just like you can freeze the model weights and then just add MLP at the end, like if it's just on one layer. And actually, the literature, they evaluated some methods like that. But we decided to use the SVM more because of the learned guarantees.
Yes, I understand that you maybe wanted to keep it simple because
Yeah.
after we can, of course, put more complex things. But I agree with you that when you use some kind of classifier that's a perceptron, a linear SPM, or other ones, not maybe it's easier in the future to explain some parts of the system, and maybe it's a motivation that you could use in the future. But I'd like also to see maybe in the future the results of different classifiers in order just to motivate the choice, maybe. But I know that's not your core, okay? It's not the core of the system. You just plug it there to show your hypothesis. But it highlighted to me why this could be a good module for your system to use this kind of classifier. Let's see if I have some questions here. I know that there is a delay between the presentation and the YouTube, but we can continue, we can move on. Thank you, Gabriel, for the presentation. And we can answer some questions later if they appear. There is a question here. Yeah, let me. Moacir, to add something to the Gabriel's answer, the idea is to use VM linear accuracy as a proxy measure for linear separability of the learning feature space. Okay, thank you, Moacir, for this a possible explanation to my question. Thank you. So thank you, Gabriel, again. Let's move on for the last presentation of this session. And the title is BR Cars, a dataset to fine-grained classification of car images that will be presented by Daniel Kuhn.
Hi, my name is Daniel and I'm going to present BR Cars, a dataset for fine-grained classification of car images. This work was done by me and Viviane Moreira. Supervised classification approaches, and especially deep learning techniques, typically require a large set of annotated data. In the context of computer vision, a convolutional neural network is a deep learning algorithm widely used for image classification tasks. Convolutional neural networks have constantly advanced the state-of-the-art in image classification tasks. And naturally, the success obtained in these general tasks led research to evaluate these image classification approaches in domain-specific classification tasks, such as classifying bird species, plant disease, or even aircraft models. And these domain-specific tasks are called fine-grained visual classification tasks. In this context, we construct BR cars. BR cars contains about 300,000 images belonging to 427 Brazilian car models. These images were collected from a car advertising website, and we organize these images into two subsets. BR Cars 196 contains images of car models that had at least 200 ads, and BR Cars 427 contains the image of BR Cars 196 and image of car models that had less than 200 ads. We may consider that BR Cars 196 has the most common car models, while BR Cars 427 is the complete version but with unbalanced classes. A contribution of BR Cars is that, unlike other datasets, BR Cars is characterized by a lack of standardization in terms of perspective, which is how images are normally presented in a number of practical applications. Our dataset can be used from different granularity levels. Granularity levels that can be used are make, model, year, or even car instance. Here we can see some statistics about BR Cars. BR Cars 196 has about 200,000 images, and BR Cars 427 has about 300,000 images. With the goal of providing baseline results, we evaluate 4 classification algorithms: Inception v3, ResNet 50, and 2 versions trained with the triplet loss function. For these experiments, the granularity level used was the car model. For more details about these algorithms, please refer to the original paper. To evaluate the classifiers, we use the traditional metrics precision, recall, and F1 measure. So, for each class, we calculated one F1 measure. To summarize these informations, we calculated the macro F1 measure. To calculate the macro F1 measure, we calculate the F1 measure for each class and then we took the average. Macro F1 is especially useful for imbalanced datasets, such as BR Cars 427, since it gives equal weights to each class. As we can observe, Inception v3 achieved the best results for both subsets. The results achieved on BR cards for 127 was lower than BR cards 196. Here we can see the F1 measure achieved by Inception v3 for each class. In BR cars for 127, the low F1 in certain classes is associated with the small number of images in the classes with fewer instances. And here we can see the classes that are often misclassified. In these cases, the models are from the same make and are visually similar. I will conclude the presentation by summarizing our contributions. We introduced BR cars, a large dataset of Brazilian car images well prepared for fine-grained visual classification tests. BR car is characterized by a lack of standardization in terms of perspective, and we perform experiments with standard deep learning classifiers to serve as baseline results for future works in this topic. Thanks for watching. Bye.
Thank you, Daniel. We have a question from Gustavo. Could you mention which practical application can benefit from BR cars?
So, hello, thanks for the question. Sure. So there are several practical applications that can benefit from our data set or even similar data sets. I can mention, for example, surveillance or monitoring applications. And imagine the situation when we need to identify a vehicle, for example, and the license plate is not well visible. So in these cases, the recognition of the car model could be useful. So there are some papers describing tracking vehicle approach using surveillance camera. So this is a situation.
Okay, we have another question from Claudio. Which laws did you use to train the models?
Function loss? What?
The laws you used to train the model. The error that you used to train the model.
So the function loss that we use the triplet function loss for when we use a triplet with an anchor image, a positive image in a false image. This was one of the function loss that we use.
And Davi Menotti also question about regarding light images. All the images are with controlled lighting.
So what is the question?
It's about the night image. Sorry, the images are all acquired using a controlled image setup, or there is some image that are at dark, or
so yeah, our images are characterized by a lack of standardization in terms of perspective. So there are images where the vehicle is not well centered in the image, or even showing only part of the vehicle. Sometimes there are shadows, and the image may contain other vehicles in the background.
and they were acquired, for instance, at indoor, outdoor, during the night, during the day, in a cloudy day or rainy, something like that. Maybe for a different situation that we could use in different applications. Maybe this is the core of the question of Davi.
Okay, so the images were using all collected in day. So, but there is this lack of standardization. So in terms of perspective.
Okay.
But our images was collected on day.
Okay. We have another question. It's from Moacir. Interesting data set. I like this idea of having multiple attributes such as the cockpit, external, as well as ear, make, and others. Just a comment, that's not a question. And I think this is all. Thank you, Daniel. Thank you for the presentation to
Thanks.
answer the question. Thank you for all the audience. That was the last paper of this section. So thank you for the questions. Thank you for the presenters. And I would like to highlight that we have keynote 5 today at 11 o'clock. So it will be very interesting. I'd like to see you there. Thank you. See you soon.